In this video, we are going to discuss the application of matrix for solving systems of linear equations with three variables. Alongside finding the solution set of the given systems of equation, we will discuss what do consistent and inconsistent system of equation mean, what do dependent and independent system of equations mean, what do row echelon form and row reduced echelon form mean. Stay with me up to the end. Let's get started. Given the system of equations 2x plus 3y minus z equal to 4, x minus 2y plus z equal to 3, and negative x minus y plus 3z equal to 6, what are the values of x, y, and z? In the given, we have three equations and three variables, so it's possible to find the value of each variable if there is. We have a number of alternatives for solving these equations, but in this section we will focus on Gaussian elimination method. Gaussian elimination method is also known as row reduction algorithm for solving systems of linear equations. The method starts by forming an augmented matrix consisting of the coefficients of the variable and the constant terms. So first let's form the two matrices separately. In the first equation, the coefficient of x is 2, the coefficient of y is 3, the coefficient of z is negative 1 because minus z means negative 1 times z, and the constant term is 4. In the second equation, the coefficient of x is 1 because x means 1 times x, the coefficient of y is negative 2, the coefficient of z is 1, and the constant term is 3. In the third equation, the coefficient of x is negative 1, the coefficient of y is again negative 1, the coefficient of z is 3, and the constant term is 6. If we insert these coefficients in square bracket, we will find a 3 by 3 square matrix. Again, if we enclose these constants in separate square bracket, we will find a 3 by 1 rectangular matrix. To form an augmented matrix of these two matrices, what we have to do is just to remove these adjacent close bracket signs and replace them by this vertical line. After forming an augmented matrix, we have to formulate formulas in order to convert these three elements, which are below the main diagonal line of the left-hand side matrix, to zeros, and the main diagonal elements to ones. Let's start from column 1. The first element of column 1, which is also the first element of main diagonal line, is 2. To convert this 2 to 1, we have to multiply it by 1 over 2. The constant term that we use to multiply these 2 has to multiply all elements of row 1. Thus, to convert the first main diagonal element to 1, we have to multiply row 1 by 1 over 2. 1 over 2 times 2 is 1. 1 over 2 times 3 is 3 over 2. 1 over 2 times negative 1 is negative 1 over 2. 1 over 2 times 4 is 2. In this first column, the elements below this 1 have to be zeros. To convert this 1 to 0, we can multiply it by negative 2 and add the product to this first row's 2. Thus, the formula that will help us to convert this 1 to 0 is negative 2 times row 2 plus row 1, and that sum goes to row 2. Negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. Negative 2 times negative 2 is 4. 4 plus 3 is 7. Negative 2 times 1 is negative 2. Negative 2 plus negative 1 is negative 3. Negative 2 times 3 is negative 6. Negative 6 plus 4 is negative 2. To make this negative 1 0, we can multiply it by 2 and add the product to these 2. So the formula that helps us to convert this negative 1 to 0 is 2 times row 3 plus row 1, and that sum will go to row 3. 2 times negative 1 is negative 2. Negative 2 plus 2 is 0. 2 times negative 1 is negative 2 again. Negative 2 plus 3 is 1. 2 times 3 is 6. 6 plus negative 1 is 5. 2 times 6 is positive 12. 12 plus 4 is 16. Next, let's convert this 7 to 1 and this 1 to 0. To convert this 7 to 1, we have to multiply row 2 by 1 over 7. Of course, that product will go to row 2. 1 over 7 times 0 is 0. 1 over 7 times 7 is 1. 1 over 7 times negative 3 is negative 3 over 7. 1 over 7 times negative 2 is negative 2 over 7. To convert this 1 to 0, we can't use its row 1 correspondence because such move will convert this 0 to some other number. Hence, the only option what we have is row 2. If we multiply this 1 by negative 7 and add the product to this 7, we will find 0. So the formula that can convert this 1 to 0 is negative 7 times row 3 plus row 2. Negative 7 times 0 is 0. 0 plus 0 is 0. Negative 7 times 1 is negative 7. Negative 7 plus 7 is 0. Negative 7 times 5 is negative 35. Negative 35 plus negative 3 is negative 38. Negative 7 times 16 is negative 112. Negative 112 plus negative 2 is negative 114. By now, these two main diagonal elements are 1s. What left is this negative 38. To convert it to 1, we can multiply row 3 by negative 1 over 38. Negative 1 over 38 times 0 is 0. Negative 1 over 38 times this 0 is again 0. Negative 1 over 38 times negative 38 is 1. Negative 1 over 38 times negative 114 is 3. We made these two elements 0 just to eliminate x and y from this third equation and solve for z. We made this element 0 in order to remove x from second equation and solve for y by back substituting the value of z we calculated from the third equation. I convert these main diagonal elements to 1s with the intent to introduce you one new concept, that's row echelon form. A matrix is said to be in row echelon form only if it fulfills the following three requirements. The first requirement, a zero row, if there is, comes at the bottom. A zero row is a row containing all elements 0. We don't have this kind of row in this augmented matrix. The second requirement, the first non-zero element in each non-zero row is 1. In this augmented matrix, the first non-zero element of row 1 is 1. The first non-zero element of row 2 is 1. And the first non-zero element of row 3 is also 1. Meaning, this augmented matrix fulfills the second requirement. The third requirement, the number of rows preceding the first non-zero element of each non-zero row except row 1 is greater than the number of such zeros in the preceding row. We don't have 0 preceding to the non-zero element in row 1, but we have one such 0 in row 2 and 2 zeros in row 3. This augmented matrix also fulfills the third requirement. Since this matrix fulfills all the three requirements, it is in row echelon form. Another terminology that is related with row echelon form is row reduced echelon form. A matrix is said to be in row reduced echelon form if it fulfills the following two requirements. One, if it is in row echelon form. The second requirement, the first non-zero element in each non-zero row is the only non-zero element in its column. In this augmented matrix, the first non-zero element of row 2 is 1, but this 1 is not the only non-zero element in its column because this 3 over 2 is different from 0. This first non-zero elements of row 3 is also not the only non-zero elements in the third column because this negative 3 over 7 and negative 1 over 2 are different from zeros. Therefore, this augmented matrix is not in row reduced echelon form. To convert it to row reduced echelon form, we have to carry out some elementary row operations in order to convert these three elements to zeros. Let's rewrite the equations by using this augmented matrix. This first column stands for the coefficients of x. Second column stands for the coefficients of y. The third column stands for the coefficients of z. And the fourth column stands for the constants. 1 times x is x plus 3 over 2 times y is 3 over 2y. Negative 1 over 2 times z is minus 1 over 2z equal to 2. 0 times x is 0, so no need to add 0. 1 times y is y. Negative 3 over 7 times z is negative 3 over 7z equal to negative 2 over 7. In row 3, 0 times x is 0, 0 times y is also 0, 1 times z is z equal to 3. This system of equations is equivalent to the given system of equations because we derive it from a given equation by conducting elementary row operations. From this third equation, we know that the value of z is 3. We can plug in the value of z to the second equation and solve for y. That's y minus 3 over 7 times the value of z is 3 equal to negative 2 over 7. Negative 3 over 7 times 3 is negative 9 over 7. Taking negative 9 over 7 to the right of equality sign gives us positive 9 over 7. So the equation becomes y equal to negative 2 over 7 plus 9 over 7. The denominators of both fractions are the same, that's 7. So we can simply add the numerators. Negative 2 plus 9 is 7. Hence the fraction becomes 7 over 7, which is equal to 1. Again, plugging the values of y and z to equation 1, we will find x plus 3 over 2 times y means 1 minus 1 over 2 times the value of z is 3, which is equal to 2. X plus 3 over 2 times 1 is 3 over 2 minus 1 over 2 times 3 is 3 over 2, which is equal to 2. 3 over 2 minus 3 over 2 gives us 0. Thus the value of x is 2. If we had reduced this augmented matrix to row-reduced echelon form, we wouldn't have gone through these back substitution steps because in row-reduced echelon form, the only non-zero constant in row 1 is the coefficient of x, and that is 1. So whatever the value we find here is the value of x. Also in row 2, the only non-zero constant is the coefficient of y, that's also 1. So whatever the value at this right-hand side is the value of y. Hence, in solving such questions, you can use either row echelon form with some steps of back substitution or row-reduced echelon form, whichever seems convenient for you. The solution set of the given equations is x is 2, y is 1, and z is 3. Gaussian elimination method is also applicable for determining certain values of which the given systems of equations have one solution, no solution, or infinitely many solutions. Let's see such application with this system of equations. For what value of k does this system of equation have a unique solution, no solution, and infinitely many solutions? Again, let's start by forming this augmented matrix containing the coefficients to the left of this vertical bar and the constant to the right of it. To convert these two, which is the first element of the main diagonal line to 1, we have to multiply row 1 by 1 over 2. That product goes to row 1. To convert these 2 to 0, we can subtract it from these 2. So the formula that can convert these 2 to 0 is row 1 minus row 2. That difference goes to row 2. To convert this negative 4 to 0, we can multiply these 2 by 2 and add the product with negative 4. Thus the formula that can convert this negative 4 to 0 is 2 times row 1 plus row 3. That sum goes to row 3 of the new matrix. 1 over 2 times 2 is 1. 1 over 2 times 4 is 2. 1 over 2 times negative 2 is negative 1. 1 over 2 times 2 is 1. 2 minus 2 is 0. 4 minus 3 is 1. Negative 2 minus 1 is negative 3. And 2 minus 1 is 1. When we come to row 3, 2 times 2 is 4. 4 plus negative 4 gives us 0. 2 times 4 is 8. 8 plus negative 5 is 3. 2 times negative 2 is negative 4. Negative 4 plus k square minus 6 is k square minus 10. 2 times 2 is 4. 4 plus k is simply k plus 4. This element is already 1, so no calculation needed in row 2. In row 3, we have to convert this 3 to 0. To do so, we can multiply this 1 by negative 3 and add the product to 3. Thus, the formula that can convert this 3 to 0 is negative 3 times row 2 plus row 3. We can copy row 1 and row 2 elements as they are because we will not make any change on them. Negative 3 times 0 is 0. 0 plus 0 is 0. Negative 3 times 1 is negative 3. Negative 3 plus 3 is 0. Negative 3 times negative 3 is positive 9. 9 plus k square minus 10 gives us k square minus 1. Negative 3 times 1 is negative 3. Negative 3 plus k plus 4 gives us k plus 1. These two elements decide whether the system of equation has a unique solution, no solution, or infinitely many solutions. The system has a unique solution if it has the form like this. That's only when these two elements are non-zero constants. In other words, for the system to have a unique solution, k square minus 1 should be different from 0. That's k square minus 1 not equal to 0. This implies, by completing the square method, k square minus 1 means k plus 1 times k minus 1. That should be different from 0. This multiplication is not equal to 0 only when k is not equal to 1 and k is not equal to negative 1. To generalize, for any value of k other than negative 1 and positive 1, the system of equations has a unique solution. The system of equations that has at least one solution is called consistent system of equation. Consistent system of equations that has a unique solution is called independent system of equation. Therefore, the system we can find for any value of k other than positive 1 and negative 1 is consistent as well as independent. If k equal to negative 1, the only change will be in these two places. If we substitute negative 1 in place of k, negative 1 squared is 1, 1 minus 1 is 0. For this equation, negative 1 plus 1 is also 0, meaning 0 equal to 0. This is always true. Thus, if the system of equations has this form, it means the system has infinitely many solutions. If the system has infinitely many solutions, it is called consistent and dependent. The other possibility is if k equal to 1. Still, the change will be in these two places. 1 square is 1, 1 minus 1 is 0. For this equation, 1 plus 1 is 2. That means 0 equal to 2, which is not true. In other words, the system has no solution. Such system of equation is called inconsistent system of equation. To summarize, if the system has a solution, we call it consistent system of equation. If not, inconsistent system of equation. Consistent system of equations are two types: independent if it has only one solution, and dependent if it has infinitely many solutions. This brings the end of part 14. Please subscribe, like, and share the page. Stay safe.